My name is Nader Haghighipour. I'm a professor of astronomy at University of Hawaii and also the president of Division of Planetary Science, Hawaii. I have the pleasure of being here tell you about planet formation. And I want to start by saying that if I was going to give this talk yesterday, I would start by talking about our solar system and try to use our solar system as a model of planet formation, develop a model for formation of our solar system, and then apply that to other planetary systems. That's what the theorists do. The reason for it is that solar system is the best system known, is the system we have known for centuries. We have a very good knowledge of it, and we have developed a lot of models for its formation. And then come a lot of other systems, 4,000 or 5,000 other planetary systems. And what do? We are not going to go back and pull ourselves out and say, no, I'm going to start from the beginning and I'm going to develop a planetary model that includes all that and explains everything. We are going to use what we have and then try to tweak it to fit every one of these things. That's the general practice. But today, actually last night when I was making this talk, I was looking at the talk that I gave in Vietnam, and I'm like, no, I'm not going to give that. This time I'm going to do it entirely differently. I'm not going to tell you about how planets in our solar system form and how I'm going to apply that to any of those. I'm going to tell you that those are telling us that it's time for us to get away from solar system and pay attention to them. There are 5,000 of them. Each one of them plays a different story. And it is our responsibility, theorists, to look at them and say, what are they doing and why they are there. So what I'm going to do today is that instead of solving a solar system for you, I'm going to start by this, and I'm going to let physics carry us. I'm not going to talk about any model. I'm not going to promote or demote or dispute any model. I'm not going to talk about any of these things that you have heard. I'm just going to let physics carry us along and see what comes out of it. And whatever comes out of it is general, can be applied to 5,000 planetary system, or can be applied to it. You see all these pauses that I have because I was up until 5 in the morning. So please bear with me as and I'm heavily jet lagged. So please bear with me as I go through this, and I'm a little bit shaky. So okay, we start with what? We start with that. We start with the molecular cloud. The molecular cloud collapses. You saw the very last slide, the previous presentation. The molecular cloud collapses. There is a radiation going, bipolar radiation, and then you end up with a nebula, and that nebula is where planets form. That's what we all know. I'm not going to go through that, but I'm going to show you this, so you know that what I just said is not it's just not out of my imagination. Molecular clouds do collapse and stars do form, and as it's going to zoom in and you'll see that disks will form and everything, and disks have a specific structure, and that structure is what carry us through what happens to them and what are the next phases. This is one of the simulations of stellar formation from Matthew Bate. So you see what is happening there. I'm going to continue it. So you see what's happening there. Stars form, disks form, stars collapse and hit each other and all that. All that good stuff. But at the end of the day, you have disks forming around the stars, and that disk has a certain structure. There is a bipolar outflow that clears surrounding of the disk and leaves you with a disk that has gas and dust in it. And that gas and dust has specific structures. Out here are regions that we believe cometary objects formed. Closer in, there are regions that believe that terrestrial planets form and all that. But the bottom line is that you end up with, after the formation of the star, after the collapse of the molecular cloud, you end up with a disk of gas and dust. And if you don't believe me, there you go. That's where they are. And this is the birthplace of planets. Planet formation starts in this environment. After that bipolar radiation goes away, you end up with a disk of gas and dust. And planet formation starts in this environment. But depending on where you are, the physics varies. What is important to know is that Planet formation occurs in the midplane of this disk, and that has specific implications for a planetary system. If you see a planetary system with one planet here, one planet over there, one planet over there, those systems did not form in a disk. Those are consequence of dynamical evolution. So the last slide, the previous simulation, right here had Pluto at 17 degrees. That did not form in the disk of the solar system, period, right? Because that is where planets form, and that is where they stay. If you see that one planet goes in 30-degree inclination, that is the consequence of subsequent post-formation dynamical evolution. It has nothing to do with the formation of the planet. That's physics, and it has absolutely nothing to do with our solar system. You have a disk of gas and dust, and this disk of gas and dust behaves in a certain way. The dust molecules are constantly subject to being bombarded by the dust particles constantly subject to being bombarded by gas molecules. And that has a consequence. The consequence of it is that the onset of planet formation, that is the coalescence of dust particles and the growth to larger bodies, is a natural and inevitable consequence of the formation of the nebula. If you have a gas and dust, I will show you why. If you have a system of gas and dust particles will come close to each other, will sit next to each other, and will grow. There is no question about it. So if you say that if that's what it is, every system must have a planetary system. The story of planetary system is not the story of planetary system is not that dust coagulation. The story is that whether that process can succeed to form a complete planetary system, can continue successfully to form a planetary system. And that has to do with the environment where it is. If you have your disk in an environment where it's subject to many perturbations, you may actually be able to grow dust particles, but you may not be able to form planetary systems. Or if you have an environment that the objects grow to a certain size, you may have a bunch of protoplanets going around, but they never succeed to form planets. This is inevitable. Whether this becomes planetary system is a different story, and that's what I want to carry you along to see what is the physics of different parts of it. The first part of the physics comes from here. What you see here is the stopping time on vertical axis in terms of the distance in the disk. So what does it say? This corresponds to radii and the size of different objects. What it says is the following. Take an object of any of that size, and only that object, put it in a disk of gas that is rotating around your central star, and nothing else, and give it a flick. That object starts by going on Keplerian orbit, and that is the Keplerian time over there. This says how long it will take for it to stop in independent motion and start going with the gas. So you see that for a micrometer object, the time is very, very short. That's the time. The time is very short. But as the object grows, it shows its independent motion, and the time of interacting or getting affected by gas becomes smaller and smaller. If you have a kilometer size, it takes a long time for gas to actually stop it and do something with it. So this tells you something very, very important. If you have a dust particle in there, the dynamics of the dust particle is heavily dictated by the dynamics of the gas. Basically, dust particles don't behave on their own. There are three ways that dust particles move in a gas. Depending on their sizes, if their size is between 1 to 100 micrometers, the Brownian motion kicks in. The Brownian motion, you're all familiar with it. A drop of ink in a glass of water, come back tomorrow, and the water has the color of the ink. That's the Brownian motion. And the differential drift is, depending on the size of the object moves because it is a solid body as opposed to gas particles, gas molecules. And the turbulence. The turbulence affects the different size of the body. I'll explain in simulations that how this turbulence causes objects of different sizes to be separated from one another. But these are the ways that dust particles behave in a gas depending on how gas dictates it, how gas tells them what to do. Now what is interesting is that regardless of this, when dust particles are in a gas, as I said, their motion is heavily dictated by the gas. You give them a flick, quickly they lose their independence and start rotating with the gas. However, there is a difference between gas motion and solid motion. Gas motion is dictated by the internal temperature and pressure properties of the gas, whereas the solid motion is dictated by the gravity of the central star. So although your dust particles are heavily perturbed by the gas, and they're dictated what to the gas tell them what to do, because of the gravity of central star, they have slightly, very slightly different motion. Two dust particles, they gently move in a gas medium, and when they come very close to each other, the molecular forces kick in and hold them next to each other. And those two form a bigger, slightly bigger object, moves a little bit faster, and once it catches another dust particle, they come to each other and they sit next to each other because of the molecular forces. And that way you start from two dust particles, you form a little bit bigger one, a little bit bigger one, a little bit bigger one, and eventually you form an array of dust particles that they're aggregates, they're fluffy aggregates. They're just sitting next to each other simply because of molecular forces. This is not just, this is what you see in experiment as well. Our colleagues in Germany, Jürgen Blum and his lab do this on a regular basis. What you see here is that a bunch of silicon gray put in a solution and letting them interact with one another, and they form this fractal type of objects. We're talking about very, very, very small dust particles, micron size, and even when they come next to each other, their sizes become 10 micron size or 50 microns or higher micron size. They're still, these fluffy aggregates, these fractals are still very, very small. And because they are small, they still gently move, and when they hit each other, they merge. Depending on whether they move fast or they move slowly, depending on how the impact velocity is, they either just come sit next to each other, or they hit each other and they just go away. They destroy each other. And then the next step is that, I can just show it with my hand, they just come hit each other, and some of them roll into one another. This process of rolling, hitting, destroying, and rolling again, this continues until you get objects of about a few millimeters. This comes right out of physics. We can actually write the equations for it, solve it analytically, and we can do it in the laboratory. That's nothing to do with simulations. This is real physics. You start from micron size, and you let gas carry you, and you naturally form millimeter size objects. So what happens next? Now you have started from small size, you grew to a little bit bigger size, and that object now shows its independent motion, goes a little bit faster. The time for its stopping, the time for being affected by gas extends, becomes larger. So what happens now is that because the object has, you rolled it and it became compact. Now the object has compactified, it's become really hard. When it goes around, it no longer, and it goes faster, it's no longer, when it sees another object of its own, it's no longer molecular forces that keep it next to each other. When they go around, they bang into each other. And that starts happening from about the millimeter size, or about half of centimeter size. And that causes problem. The problem is that when you do the similar type of experiment and you let objects of half a centimeters or centimeter size hit each other, they don't stick to one another. They actually break each other. They move so fast that when they see each other and they hit, they break. What you see here is the radii of two objects hitting each other with different velocities. The color coding indicates whether these two objects will stick to one another or not, and what happens to them. Red means fragmentation, and orange means cratering and erosion, and green means sticking. So if you have the unit is centimeters, so if you have objects of about a % of centimeter or smaller, when they see each other, the molecular forces kick in and hold them next to each other. So the sticking is actually okay, it works out. But as any of the objects, they grow in mass, when they get to larger region of the parameter space, then sizes become larger. When they hit each other, then the erosion and fragmentation kick into place. So you ask yourself, physics dictates how things go, and that physics grow things for you to about a centimeter size, but then the same physics fails you. And then past centimeter size, you cannot continue. So how did planets form? And the problem is that it doesn't even end here, it becomes even more complicated. Now what you see is the same interaction of gas, solid with gas, except that what I'm showing here is the relative velocity with respect to gas for an object in terms of its size. This is the size of the object, and that is its velocity relative to gas. As an object grows, its interaction with the gas and the type of the gas drag changes. So you start from one regime and you go to another regime as the size of the object grows. And then once you do that type of simulations, you'll see that objects of about meter size don't respond to gas drag well. As a matter of fact, gas drag, instead of taking energy out of them, causes them to migrate toward the central star and get dumped into the central star. So what is the problem? The problem is that you start from centimeter size, you grow them to, you start from micron size, you grow them to centimeter size, and they don't stick anymore. They stop right there. Even if you could grow them larger to meter size, then they wouldn't stay around for you to form planets. They get dumped into the central star. So you ask yourself, how did planets form? Well, I put this slide in just as a summary of what I just explained, that depending on which part of this nebula you may have drift towards the central star, you may have coagulation to the larger bodies, you will have a settling on the midplane because planets form on the midplanes and all that. It basically summarizes what I just explained. So, how did centimeter-sized bodies grow to larger sizes? I'm going to be very, very, very honest with you. This is honest-to-God answer. We don't know. Seriously, we do not know. You may have heard of all these fancy models and everything. Every single one of those models comes with assumptions. Every single one of those models comes with simulations that are limited to computer capabilities and all that. And at the end of the day, you may have a model that can explain things for you at that region of the disk, but it may not be able to explain everything within the context of the solar system. So, there are models out there. I said that I'm not going to talk about any model. There are models out there, and you can study them as much as you want. But at the end of the day, we really don't know how this growth happens. One thing that I can tell you is that, in my opinion, nature has the tendency of identifying the most logical and physically valid way and take that route. So if we are going to model, we better not make it too complicated. Complicated models are really, really nice. They do a beautiful job on our computer, but they do a beautiful job on a computer. In the reality out there, complicated models don't last. Simple as that. Nature is not going to do it the way that we do it. Nature is not going to solve all those fancy equations. Finds the way to go. One thing that I can tell you for sure is that when the disk is there, the disk evolves into become turbulent. So these turbulences and the places where this turbulence happens may help bringing objects together and facilitate their growth to larger bodies. And that is because of a very nice physics that occurs when this type of things appear in a disk. So the turbulence causes that in some regions of the disk, the density of the gas is locally enhanced, or pressure of the gas is locally enhanced. And that results into a very nice physics things. So what I'm showing you here is what I made of gas, and I made the density of the gas at this ring to be a little bit more than its surrounding area. The gas also has dust particles in it, or solid objects in it. Solid objects are subject to gas drag, and also they're subject to the gravity of the central star. Gas itself is subject to internal pressure, and because of its internal pressure, it expands until the gravity of the central star and internal pressure, they counter each other, and then the gas reached the equilibrium, static equilibrium, right? At that stage, the equation of the gas is given by this. Its rotation is because of the gravity of the central star and because of its pressure. The pressure and gravity counter each other, and then gas reaches equilibrium and it starts rotating. For the particle, however, you don't have pressure. You only see the gravity of the central star. So the particle goes on Keplerian motion. That causes something very interesting. If a particle is out here, outside of a pressure bump or a density inhomogeneity or a density accumulation, the gas density accumulation, when the particle is here, then what happens is that when it's moving, the gas is going slower. You know, when you're outside, outside of the pressure bump, this is high school algebra, that derivative is negative, right? And because that derivative is negative, if you are going Keplerian, gas is going to go slower. So the solid object goes Keplerian, gas is going slower, is going to prevent the solid object to go fast. And what happens is that the solid object loses energy and momentum and spirals inward. Inside of this density, what happens is that derivative becomes positive. So when it is positive, the gas molecules that is inside goes faster. So if you are a particle and you are going around the star with the Keplerian, gas is pushing you from behind. So you gain energy, you gain angular momentum, and you spiral out. So if there is, even if momentarily, even if for a short time, there is some sort of pressure bump or some sort of density enhancement in a gas, that density enhancement, for as long as it lives, it brings solid objects together. That may facilitate the growth of bodies to a larger size, but it all depends on its lifetime. It all depends how long it stays around and how strong that is. When it happens in density enhancements around here and it accumulates bodies, now your accumulated object, its collective behavior is larger than centimeter size and it moves faster. So now you have sort of you can say that you have sort of overcome that centimeter size collision barrier, but now you have a bigger object that is moving, and if it hits another bigger object, it may coalesce with it or may break it apart. But what I want you to take from this is that this type of behavior that happens in a disk and is because of the evolution of the disk may enhance or facilitate bringing of objects together. But at the end of the day, we don't know how objects grow from centimeter size to kilometer size. But what we know is that disks of kilometer size exist. You all have seen images of debris disks. They are there. Debris disks that are a result of collision of bodies, they're there. They exist. They prove that objects do grow from centimeter size to kilometer size, half a kilometer. What I'm going to do is that I'm going to continue from there. So I'm not going to talk about how these objects grow, because then I will be talking about the specific models, and I promise that I'm not going to talk about models, but I want to talk about the physics. We know that the physics can carry us from dust to centimeter size, but we don't know what happens next. But what we do know is that if we have a disk of kilometer-sized bodies and a bunch of other objects, gravity will kick in. Remember this. Now what happens is that when you go from this regime to regime of kilometer size, then the effect of gas is much smaller. Gravity is the dominant effect, and that gravity causes objects to interact with each other through mutual gravitation, right? And that we know how to do. We know it. We know force equals mass times acceleration. Force is force of gravity. We can solve that equation. So the rest of it comes out of physics and algebra. Now what I'm going to do is I'm going to explain a few things that we do in celestial mechanics, and then I'll tell you, with that explanation, I tell you how we go from here to we grow, objects grow and become bigger and bigger. Take one of these bodies. For instance, take this one. So this object has its own gravity, right? We define a sphere around it. We don't define. There is a sphere around it that any object within that sphere, it will feel the gravity of this body. Their motion is basically dominated by gravity of this body, and everything else, including the central star, will be perturbation. For objects outside, the central star is the main force of gravity, and that is a perturbation. This region around that object is called Hill's sphere. And it comes from a simple formula. It has to do with the mass of the object, with the mass of the star, and the semi-major axis of the orbital of the object. So anything inside this radius, will be dominated by gravity of the object, right? So if you have a bunch of smaller bodies here, the gravity will attract those toward them because the rest of the world is just perturbation. The gravity of this body starts attracting them. They come rapidly, they come towards that little kilometer-sized object, and they stick to it, and the mass becomes bigger. And once this mass becomes bigger, that radius becomes bigger. It encompasses more material. And more material gets attracted to now a slightly larger body and stick to it. And the mass becomes bigger, and the radius becomes bigger, and attract more material, and this whole thing goes through what is called runaway growth. You start from kilometer-sized bodies, and by simple gravity, your object in a very short time grows to become bigger and bigger and bigger. As this process goes through, the objects around, same thing happens to this one, same things happen to that one. Objects around get absorbed by other bodies, and eventually you end up with a bunch of bigger objects that have swept up the surrounding area, and they become bigger and bigger. Now something interesting happens to them, and now remember we are at the regime that gravity kicks in. So these big objects, they interact with each other through gravity, and they go around, they hit each other. They are moving really fast, they hit each other, they break each other into pieces. Again, they sweep each other through the process that I just explained. They grow, they hit each other into pieces, and this process constantly continues until bigger objects are formed. You will have a disk of big moon-to-Mars-sized planetary embryos, kilometer-sized bodies, dust, gas, and now you have a soup of the material, which its dynamics is primarily dominated by the center of the star and the gravitational force of these big objects that form through the runaway growth. So far we are good. Now let's see what happens when this process that I just explained occurs at different parts of the disk. I'm showing this cartoon. On one side I'm showing the change in the temperature of the disk. On the other side I'm showing the type of the material that may grow in that object, in that disk. Okay. So let's for a moment focus in the region where the material, the disk contains ice. So as you go farther away from the center of the star, the amount of ice that originally existed in the disk stay. You can define a region that is called the snow line, and then past that the disk basically maintains its ice. Now before I continue, I want to say something about the snow line. We all talk about the snow line, but I want to make it a little bit precise so we know what actually it is. The snow line is a place where in a gaseous disk, in a nebula, the dust particles manage to maintain molecules of water on their surfaces permanently. If you have a fully formed planetary system, there is no snow line. You can define a region beyond which the lifetime of the ice changes by the distance. You can define ice longevity region, but there is no snow line. Our solar system does not have a snow line. We have water here, right? But right past us, past Mars, all those asteroids, many of them are dry. So how do you define that? In a fully formed system, we define ice longevity system, ice longevity model. You can say that depending on where the object is, it can maintain its ice for a certain amount of time. There are models for that, and they work perfectly. When you are dealing with a nebula, you can define a snow line. You can say that past that region, the dust grains can maintain ice and water molecules on their surface permanently. So if that's the case, if you are dealing with objects here, if this process of growth and runaway growth happens down up here, something interesting occurs. So here your objects are primarily, carry primarily ice. Remember, this whole formation, let me go back here quickly. This whole thing is local. You are here and you absorb whatever is in your surrounding. When you are here, you are not absorbing anything back here, right? Because it is local, so if this happens back here, most of the material that goes into that object is ice. So now you're dealing with a bunch of objects that have dirt and ice to them, and they go around, and as they go around, when they hit each other, they stick better. So bodies containing ice stick more efficiently, and as a result, when they stick, they grow better, they grow more efficiently, right? So as a result, the runaway growth produces large bodies in the part of the protoplanetary states in a short time. So when you're out here, when your objects have ice on them, you stick better and you grow them better, or they do, they grow better. And what happens is that you form a bunch of big, large bodies, larger than those planetary embryos in a very short time, right? Now, when that occurs, three things can follow. The first thing is that those bodies that are growing, those planetary embryos that are now growing to become, say, moon, Mars size, 10 Mars size, half of Earth and all that, they interact with each other, they throw each other out, or you end up with a disk that has a bunch of small bodies and everything. Some of the Kepler systems are like that. And, or no planet formation occurs. Simple as that. You know, your disk just forms the small bodies and everything goes away. The other possibility is that one body or two, they become large enough to attract gas from the surrounding. So they grow, the system allows one or two or three of them become so large that as they're growing, they start attracting gas from their surrounding. So I'm going to show this, but don't read much to it. I'm just using it as a cartoon. So you have your object sitting out there, and it has grown enough to start attracting gas. So it goes through the similar process of runaway growth. The object attracts gas, and as it attracts gas, it has more gravity, attracts more gas, and it goes through a huge process and attracts a tremendous amount of gas from its surrounding and sweeps up all the material in its path. Now the gas becomes so heavy that it cannot stand its own gravity, it collapses, and it collapses, stops until the gas reaches equilibrium. That is when you have a gas giant planet. That's what it says here. Your solid material in the disk grows until the point that it has enough gravity to start attracting gas. And it starts attracting gas without its solid growth changes. And then the gas accretion becomes rapid, goes through a runaway growth, and then the gas collapses and you get your giant planet. Notice that I didn't mention any model. Notice that I didn't put any time scale on it. This comes out of physics, assuming or provided the disk allow that to happen. If the disk does not stay around long enough, if the gas does not stay around long enough, and if the third thing happen, you will not have that. And the third thing that can happen is that as that object starts growing, as the solid growth at this region is happening, the gas is still there. And that gas can apply a torque to the object. The part of the disk of the gas that is interior to the object wants to pull it this way, and the part that is outside wants to pull it that way. Depending on which one of them wins, the object may move. That motion, that migration may happen during the formation or may happen after the body formed, depends on the characteristic of the gas and the disk. And what happens is that you will have planet migration. And that explains all these hot Jupiters and warm Neptunes and all that you have. They form. They have no choice but to form in the outer part. That is the part that physically allows and facilitates growth to larger bodies. But then because of the subsequent interaction with the disk, they have no choice but to migrate. So they migrate. They either migrate by opening a gap or they migrate as they're growing, depending on the type of their system. So you may ask that, okay, if this is the case, every giant planet has to migrate. Why didn't our solar system migrate? So before you bombard me with all that question, here we go. Planet formation is a stochastic process, period. It's a stochastic. There is nothing we can do about it. And that means it is not possible to regulate it, nor is it possible to make predictions about it. We may make a model, but we are making a model in our computer, assuming that nothing else exists except for our model. In reality, a molecular gas that collapses is subject to a lot of perturbation from the rest of the universe, from the rest of the galaxy. Who knows what happens to it? We don't know the initial conditions of any of our planetary systems, and we don't know the dynamical history. We just model them in our computer, assuming that our system is only that and nothing else exists in the universe. So you see how limited those models are? I've been doing that for 25 years. I can see, I can say that, you know. I can say that what we are doing is limited. What we are doing has a lot of shortcomings in it. But I want you to also see that what these shortcomings are. And of course, some of it comes because our hands are tied, you know. We are limited with our computer capabilities. But at the end of the day, we know that even though we model planet formation, we know that it is not possible to regulate it and it's not possible to make predictions. So you ask, what's the point of doing all this? Well, the point is the following. Do a lot of it and identify the physics that is most dominant. We do a lot of planet formation models with different type of physics, and we do a statistical analysis to see which one of those physics processes is the most dominant and in what system. So far, I've been trying to familiarize you with the different physics that kicks in from the beginning, and I'm carrying you all the way to what happens when Earth is formed and all. So you see the different physics processes that come in. But at the end of the day, what we do is that we take our computers, we see how much we can do with it, and we start doing that. We start doing putting physics in our models, and we run simulations after simulations, and we run 2,000, 3,000, 5,000 simulations, and we study them statistically. That statistical analysis tell us that, yes, if your gas stays around, there is a very good chance that your system will actually make giant planets, despite the fact that observations say giant planets are rare, right? So it, you see what I'm trying to get at? I think I keep repeating myself. So let's go back here. I explained what's going on back here. Okay, now I want to explain what's going on there. What if this whole process of runaway growth happens there, in a region of the disk where the disk has already lost its water because it's close to the central star, and the building blocks of planets are dry? What happens there? Well, in the inner part, planetesimals dry and they rotate rapidly, and as a result, they collide and they shatter and fragment each other. So they move very rapidly, they're a bunch of rocks, they run into each other, they shatter each other, and they break each other into pieces. So you ask, why do we have Earth? And why do we have terrestrial planets and all that? Well, let me explain that see if I can use that simulation to explain this. Okay. So what you see here, what we use to explain terrestrial planet formation in a very simple way without doing much of modeling. So you see the green and the blue dots. The green dots are the products of that runaway growth that resulted into planetary embryos to Moon and Mars-sized bodies. And the blue ones are those kilometer-sized planetesimals that are there because these bodies hit each other, they break each other into pieces, or they did not form planetary bodies. Remember, as I was talking about this the runaway growth, I said that you end up with a disk of Moon to Mars-sized bodies, kilometer-sized object, dust, gas, it is all there, and that rest of it is represented by those kilometer-sized bodies. We put them over there. We let all these 3,000–4,000 objects interact with each other through gravity. And we literally solve F equal ma for all of them. We don't force them, we just put 5,000 equations over there and we say to computer, solve this, right? So if you have a good computer code to do that for you, then if you you'd say to a computer one other thing, that when the objects hit each other, how to treat them. So that I will explain. That is one of the limitations that we have because of our computer capabilities. Depending on how you define when objects hit each other, you can go from one time to another time to another time and integrate your system forward, and eventually you end up with a planetary system. So you let objects hit each other, and they interact with one another, they interact with those planetesimals. Everything is gravity, right? Everything is g mm prime over r squared. You know, simple physics 101. And you end up with some assembly of planets. Now, see what I wrote over there. If giant planets in the outer part of the disk do not undergo major migration, collision among planetesimals and planetary embryos may result in formation of terrestrial planets. And I bolded may and terrestrial planets because depending on the terrestrial planet formation, or any planet formation is stochastic. This may not produce anything, or it may produce 1 or 2 or 5 or 10 objects of different sizes. But it doesn't mean that if you put that over there, you will always get something like this. It's a stochastic, and you may not get anything at all. But I also wanted to mention major migration. If the giant planet, as it is forming, migrates, then it affects whatever is in front of it. And that effect, depending on the rate of the migration, depending on the size of the giant planet, that the perturbation that is imposed to the material in front of it will cause different type of systems. For instance, your giant planet can migrate and become a hot Jupiter, or if the disk goes away at a certain point and it stops, it can produce super Earth, or it can produce come close and it can produce some terrestrial planets, produce variety of things depending on how it migrates, how large or small that is. So once again, stochastic. Stochasticity is the name of the game, and you can see it depending on your system, you get different results. So despite the fact that it's stochastic, despite the fact that you can't use it to make predictions, something interesting comes out of it, and that's what this is what the slide is about. We made this slide assuming that Jupiter and Saturn are in their current orbits, and actually Andre, sitting all the way back, was kind enough to make this slide. So Jupiter and Saturn are sitting on their current orbits, and we put this bunch of planetary embryos and all that in the inner part of the solar system, and we let them interact with the star, with Jupiter and Saturn, and with one another. And this is one snapshot after 1 million years. So let me explain to you what this is. These lines that you see here, this correspond to mean motion resonances with Jupiter. Any object that gets to this line, its orbit will be half orbit of Jupiter, or when it gets here, the ratio of Jupiter, or orbital period of Jupiter to orbital period of this object is 7:4. It gets to mean motion resonance with Jupiter. This thing that you see here, and we show by nu6, is the perturbative effect of Saturn. Is because of secular effect of Saturn. And the same thing down here, nu5, is because of secular effect of Jupiter. What does the secular effect means? In a very, very short sentence, as Jupiter and Saturn rotate, the variation of their orbit imposes perturbations on the variations of orbital asteroids, and that causes some of the asteroids to gain high eccentricities. What you see here is eccentricity of the asteroid in terms of their distance. Okay, this is a snapshot of the interaction of a disk of planetary, protoplanetary objects and asteroids with Jupiter, Saturn sitting there in their orbits. This is the signature of those objects. If your disk, if your system, if your final planetary system carries the signature of the perturbation of giant planets, that tells you where giant planets are. That tells you where giant planets were at the time of the formation of the system, right? Now let's look at our solar system. This is Kirkwood gaps in our solar system. What you see here is the number of asteroids in terms of their distances, in terms of their semi-major axis, and there are gaps. This is the bird's eye view. There are gaps in the asteroid belt, and those correspond to mean motion resonances with Jupiter. And these are the effects of secular resonances of Jupiter and Saturn. For instance, Saturn causes the inclinations to be below 20 degrees and not to exceed 32 degrees inclination of asteroids. You see this, and as I mentioned, when I was explaining the formation of objects in the outer part and inner part, the outer part formation is much more efficient and happens more quickly. This shows our solar system when it formed. Jupiter and Saturn were where they are now and affected the formation of terrestrial planets. So you may not like that, and you might have seen many models that move Saturn and Jupiter and all that. At the end of the day, before terrestrial planet formation is complete, your Jupiter and Saturn have to go back to where they are now to produce asteroid belt and to produce the secular and secular effect that we see. Asteroid belt is the evidence, carries the signature of where Jupiter and Saturn were at the time of the formation of terrestrial planets. So no matter what type of model you develop for the formation of solar system, your terrestrial planet formation is heavily affected by the fact that Jupiter and Saturn were where they are now at the time of the formation. So this has a very important consequence. Accretion is local, and objects form from whatever is their surrounding. Remember the slides from the runaway growth and everything. So if that is the case, and if Jupiter and Saturn were sitting over there when terrestrial planets form, Earth formed in a region of the protoplanetary disk where originally there was no water. This is a cartoon, Earth formed around here, right? And that region was originally dry. And accretion is local, Earth formed from dry material, so where did the water come from? Okay. And that all has to do with the evolution of our solar system, the formation of the giant planets and all that. So let's go back to here. You look at your disk and say, Earth formed in a dry region, and this disk shows that the reservoir of ice is back here. So is it possible that icy objects from the outer regions somehow found their way to Earth, and they got added to the surface of the Earth after Earth was fully formed, and that way water was delivered? Well, if you do the math, the answer is not enough of it will come in. There are different models for the amount of water that is on and inside Earth, and if you take that into account and do the math, the number of objects that can come from the farther out to the region of Earth, you see that at best you can bring in 10% of the water. You still need to account for about 85–90% of it in some other way. So can this happen? In reality, yes, but it doesn't bring enough of it. So you ask yourself, what happens next? So this is the idea. Where objects like comets, planetesimals from farther regions, did they bring water in and add it as a veneer to the surface of Earth? Well, the problem with it is that they might have, except that when you look at the chemical properties, they may not agree with the chemical properties of the current ocean water. This shows the D2H ratios for different comets and also the D2H ratio for Earth water, protosolar nebula, and also for the next table also for meteorites. So you see that those comets that could have come around Earth and be close to Earth, their D2H ratio doesn't match that of Earth. This table shows that as well. I'm going to just box this so you see that the nebula and carbonaceous chondrites and Earth, the carbonaceous chondrite and Earth are close. Nebula is much smaller, and they're different from comets as well. So you ask yourself, where did the water come from, and why is it that this whole thing doesn't work? Well, before I get into the next phase, I must mention that I said here the argument for comets not being the major source of water is that the D2H ratio doesn't match the D2H ratio of the current ocean water. But we have to take that with a huge amount of caution. The current water that we have is not primordial water. The current water on ocean has been diluted, has been polluted by Earth, by life. And life and biology and all that has created a D2H ratio that may not be the true representative of what it must have been at the time of the formation. So while this argument is still being used, but if you're going to use it, just keep in back of your head that the current D2H ratio of the Earth water may not be the true representative of what it was at the time that it was primordial. But my argument for that is always this, that if you do the math, if you do the dynamics, if you actually do encountering of comets with the inner part of the solar system and count them, you won't be able to bring enough of it. Okay, so what happens and why is it that Earth has water? So go back again, let's go back again here. This is where water is. But what I try to explain is that whether the water can come all the way from this region to the dry region. However, as you go farther away, the amount of water may actually maintain in asteroids in the region close to the terrestrial planet formation, and that may affect the delivery of water to Earth rather than bringing something all the way from back here. What I'm trying to say is that maybe the answer to the question is not here. Maybe the answer to the question is around here. Maybe the answer to the question is in the fact that after planet formation and kilometer-sized objects are formed, during their formation, they trap some water in them, and that water stayed in them despite the fact that they are in asteroid belt, despite the fact that they are close to the star, the water inside stayed in them, and that water contributed to the formation of Earth during its formation and not necessarily after it was fully formed. This is what this type of simulation tells you. This is the same thing that I showed in previous slide. Now what I'm doing is that I'm assigning some water to to all those asteroids and embryos, and I'm increasing the amount of water as the object goes away, because you go farther away, the disk becomes cooler, so presumably your asteroid, your embryo might have been able to retain more water. And now we let them go through the same type of interaction, and the gravity kicks in, and what we see is the following, and I really want your attention here. What we see is the following. We see that objects from here, especially large planetary embryos, they hit each other, and during the collision, some of their contents, some of their volatiles, including ice, gets transferred to another body. And then they hit another one, and some of them gets transferred to another one. This transfer of water, transfer of volatiles, we see them happening through successive collisions until objects that are here receive some of that water. You start with a lot of water back there, you receive a tiny amount of it, but that is all right, because the water content of Earth is only 0.1%. It's around this amount. So you don't need to bring in much. And this successive collision, even though some of the water is lost during this collision, helps you to transport water from one place to another, and that way you can account for the water inside there. So the idea behind it is that the water was not delivered and was not distributed on the surface. The water came through successive collisions and was transferred from one object to the other, and eventually was incorporated to the formation of Earth, and Earth formed all this from these objects that had some water in them. And that way we believe that the water. So water, another thing, water was not delivered by embryos here getting tossed into that region. It was through successive collision, and I want to emphasize that because there are several points that I want to make before I finish my talk. I'm going to show you one of those simulations so I can rest my throat as we do this. So Jupiter and Saturn are sitting somewhere here, and the disk objects interact with each other. You see the effect of mean-motion resonances. You also see, let me quickly stop it here. You see that effect of nu 6 of Saturn, you see the nu 5 of Jupiter, you see the effect of mean motion resonances and all. And I deliberately, again, thanks to Andre sitting back there for making these movies, I deliberately chose one that does not give you solar system, just to tell you that these simulations are stochastic. So not just because I started with some initial condition, I should get solar system. Not necessarily. Now, for about 20-25 years, I've been showing these movies, and I've been saying that this is how solar system, terrestrial planets form, and this is how water comes about. We also went further to say that this whole process has one issue. When we use this process to explain formation of our solar system, we get Earth, we get Venus comes as a bonus, we get some asteroids, but Mars is large. We have been saying that for 25 years, that these models of terrestrial planet formation, they give you, they explain how Mars, Earth and Venus are formed, but they can't explain the small mass of Mars. Mars is too massive. We even went ahead and made theories for them. So this is a theory. This is the Grand Tack model, Walsh 2011, and Andre and I and Otten, we developed this theory, the partial gap model. And we were able to explain that, yes, if the disk had non-homogeneity in it, depending on how those non-homogeneity were distributed, where they were, you may be able to get a solar system that has a small Mars. We even went ahead and said that. But we never told you one thing. These simulations are not quantitative. And what does that mean? It means that we are using them to explain formation of our solar system, but these simulations have some internal shortcomings that does not allow them to be quantitative, and therefore cannot be used to determine how much water was delivered to Earth and whether Mars is truly massive or not. And the reason for it is a variety of different things. So there are merely, these simulations are not quantitative, they are merely for the proof of concepts. You use these simulations to identify the most effective physics, because your computational facilities are limited. So you can't do everything at all times. You have to identify the most effective physics and use that as your primary source to continue. So these, you run several hundred, several thousand of this. You analyze them statistically, and that tells you that the 4 or 5 pieces of physics are more important, and those 2, you can ignore them safely. One of the biggest issues with these models is the following. Remember when at the beginning of my talk I said when objects come close, depending on how you defined, they hit, right? Now here's the thing. Many of these simulations, not all of them, many of these simulations suffer from the following flaw or shortcoming. When objects come close, and if they hit each other, they break each other into pieces, and all of a sudden, in the first step of your integration, from 5,000 objects that you start with, you end up with about 1 million debris, right? The speed of this type of simulation goes with the number of objects squared. So in the first step of integration, you produce so many debris, so much debris, so many objects that your integration halts and you cannot continue. And all you are doing is just solving F equal ma. You cannot continue, right? To overcome that problem, what some of these simulations do is that they define the critical distance. They said if the two objects come closer than that critical distance, consider them fully merged, add their masses together, add their volatile contents together without any loss of mass, without any fragmentation, and without any loss of volatiles. So you take 2 objects, you add them together, you use simple conservation of mass and momentum, and you continue. This way, you reduce the number of the objects through the collision, and you allow your simulations to continue. Except that, so as you can imagine, I'm going to run this for you. This is what happens when the objects actually hit each other. You know, they break each other into pieces and all, and they produce a lot of debris. A quantitative model has to be able to model collisions and transport and transfer of volatiles correctly. So if you want to be able to do planet formation and understand how planet formation gets into other, what is the physics behind it and how it can explain formation of other planetary systems, we have to do collisions and we have to do transport and transfer of water correctly. Okay, so now, as I just explained to you, this simulation that you saw, that objects hit each other, these are SPA simulations. They produce a ton of bodies. You have no choice but to use SPA simulations to model collisions realistically, but as you notice, they produce so much small objects that your integration halts right there. You start with a bunch of bodies and you let all of them hit each other and you treat all collisions through SPA simulations, and boom, you produce billions of objects and just integration halts and you can't proceed. So what do? A quantitative model of terrestrial planet formation has to be able to model collision and transfer of the volatiles realistically. There are codes that they do that, and they do that by making certain assumptions. There are codes that include fragmentation based on a preset prescription. They say that I consider two objects hitting each other depending on their masses and their relative velocities. When they hit, I break them into 5 pieces, 10 pieces. They introduce some prescription. They work perfectly. There's nothing wrong with them. Some of them use collision catalogs. They say that two objects come, I look at a catalog, a preset catalog, and that catalog says, if the masses are that and the relative velocities are that, take 3 fragments, each one of them with such and such mass and relative velocity. They're good as well. So you can use those to do the realistic collision, except that all current models consider no loss of volatiles during the transport and transfer of bodies. So they do it. They do the collisions, but they work very well for the mass accumulation, not for transfer of volatiles. So why does that matter? You see, an object, you want to form Earth, an object from here is not like that. An object from here is going to go jump over there immediately and contribute to the water content of Earth. Object from here hit another one, that one hits another one, that one hits another one. This whole process for transferring volatile to the region of accretion of Earth takes tens and hundreds of millions of years. Right? You have to take that into account. Why? Because during that evolution, when two objects hit each other at this region, when two objects hit each other and one of them passes its volatile to another one, there is a time until the next collision happens, and during that time, the water or volatile content of the second body, the object may lose its water, the subject to evolution of the body. So let me explain what that means. This is what happens to your planetary embryos all the way back there. They constantly get hit by planetesimals, planetary bodies. Some of them remove mass, some of them produces craters, and some craters are deep and get ice out, right? And that ice gets exposed, and as it gets exposed, so during the orbital evolution of the body, so that's what you see here, as it gets exposed during the orbital evolution of the body, some of the ice that comes out in craters or they get scattered out, they evaporate. So two bodies hit each other. This one receives water, but it takes 5 million years for it to get hit by another body to transfer its ice. But during that time, it does not maintain its original ice. Some of the ice goes away. We have to take that into account. The realistic model has to take that into account. This is what I just explained, that you have an object, it hits, the volatiles expose, and that takes the volatiles evaporate, and what you have at the end is not what existed at the beginning. Okay, so a collision between planetesimals and embryos has to be done correctly, and that collision has to take into account the loss of volatiles and model transfer of volatiles and model the transfer of volatiles. And you also have to model the transport of volatile from one object to another. So pay attention here. You know, you have your body gets hit here. I'm a planetary embryo, I get hit and my water surfaces, right? It takes me 10 million years to get the next collision, but during that time, I'm not here. I have moved all the way here, right? During this motion, because I'm subject to a variety of perturbations, I may lose some of my water, right? That I call transport. And then the collision from one object to the other, I call it transfer of volatiles. That has to be taken into account. And what this shows you here is that the rate of sublimation varies depending on where the object is compared to sun. So sun is here. What you see is the temperature as a proxy for distance. You are farther away, the temperature is lower, and you're closer, temperature is higher. And that tells you when ice is exposed in a body, how that ice sublimates as the object gets closer to a closer region of the disk, especially during its motion. And you see that a lot of evaporation happens in this region, and this is region close to Earth, about 240K, 260K. You have to take that into account as well. And when you take all that into account, then something very interesting happens. So I'm going to run this thing. So then you have an object that carries water. You have an object, the same object carries dirt. It also has a core, say solid iron core. And these objects, these bodies hit each other, and depending on the collision, interesting things come out of it. What you see here is the collision angle up here and the collision velocity, and what is here is the water loss. How much water is lost during the collision? Some of the water is lost because it evaporates during the orbital evolution. Some of the water is lost during the collision because of the heat of the impact. Some of the water is lost because the object loses its material. You hit it and half of it goes away. This tells you that when objects hit each other, how they lose their water based on the angle of the collision in terms of degrees and the collision velocity. And you see that, of course, as expected for higher collisions, even with low angles, you have more water loss as opposed to when you have oblique angles. Okay, so I'm getting close to finish up. And what I want to say, I wanted to just show you application of all these ideas to one of these models. So we took one of our models and we identified this thing that became Earth. And then we look at its dynamical history and we noticed that it was originally at 1.5 AU and its water mass fraction was 0.5%, and it collided with 15 planetesimals and 3 planetary embryos. So we went through all this process of doing the collisions right and getting the water transport and transfer and the water evaporation, all that. We got it right, and we noticed the following. So this table is a little bit critical to explain. So this is the original water content, and this is the angle of the collision, and this is the water loss. So this table tells you that if you only merge bodies and don't consider collision, don't consider water loss during the collision, you will be overestimating the amount of mass and water into the final body, something between 40 and 63%. The immediate consequence of this is that problem, the Mars problem, is an artificial problem. It's a problem of the computer. It's not a problem of physics. It's because our computational codes, our computational tools are limited, and because of the way that we treat collision, we cannot get it right. It is not because there is a Mars problem. So when collisions treated, this is my conclusion, when collisions treated correctly, classical model of terrestrial planet formation can form solar system analogs, including Mars. We have to do the collisions right. So we are not developing theories, and we are not developing problems and then try to solve that by developing new theories based on something that is artificial. Chemical composition of planets, water contents, cannot be determined post-formation. This is what a lot of people do. They bank things together and then they go back and say, oh, where did the objects come from, right? This is absolutely incorrect. I've been doing that for 20 years. I'm telling you, this is absolutely incorrect. The content of chemical content, chemical composition, is the result of successive collisions. You have to do the collisions right. You cannot just say, I'm going to collide this and see where this object came, where that object came, and then I decide how much of it is from this, how much of it from that. It just doesn't work. Especially your volatiles, during their orbital evolution, you lose them. During the collision, you lose them, and they just go through space. So, loss of water during impact implies that at time t equals 0, the water content of planetesimal and planetary embryos were larger than traditionally considered. The traditional consideration is based on the water contents of meteorites. And that will tell you, consider 0% for interior to 2 AU, 2 to 2.5 AU, consider 1%, 2.5 AU to 5 AU, consider, say, 5%. If you do that, and if you do the collisions right, you will not get the amount of water on Earth that agrees with geological evidence. You need to start with something larger than 20%, and that immediately puts constraints on the chemical composition of the disk, the primordial disk. Observational geological and meteorite data are needed to constrain the surface density of the chemical composition of protoplanets. And that ends my talk and presentation. Thank you so much.